maybe I should do that this time. Record. See. Oh, it's already recording. It is indeed. Okay. Sounds good. Okay, so welcome everyone to this session of the Leiden-Delft-Erasmus Center for Sustainability Circular Industries talks. It's a mouthful. And thank you all for being here. And we have another talk in the series from the Circular Circuits project. And today we have Dorien. Dorien van Dolderen is going to talk about the design part of electronics recycling. And I'm really interested to hear what you're going to present to us today, Dorien. So without further ado, I'd just like to give you the floor.
Thank you. So I'm Dorien. I'm also in Circular Circuits, and I'm a first-year PhD. And that means I will try to talk about some of my results. Do you want to have a microphone on or the sound on? Okay, that's strange. I hear myself talk in a way that I shouldn't hear myself talk.
Okay.
I'm just waiting for my colleagues to figure out what's wrong.
Okay, good.
Yeah. Okay, I think this is right. Okay, yes.
Okay.
Thanks. So I will try to talk about some of my results, but because I'm just a first year, I don't have that many yet, and I will also just talk about what I'm planning to do and what I'm working on right now. So first, very quickly, I'm going through the problem that I'm sort of contributing to hoping to solve. The problem is, of course, e-waste. It's the world's fastest growing domestic waste stream, and very little of it is actually currently properly collected and recycled. And that's a problem for multiple reasons. So first, e-waste is very hazardous. And well, this is an extreme picture of informal e-waste recycling in India. That's not really what happens with the e-waste here, most likely. We don't know, of course, every system has leakages. But still, the e-waste contains a lot of hazardous materials, and there can be exposure from fumes or dust, depending on how you treat it. So in informal recycling, they might try to burn out copper of PCBs, and of course, that's very hazardous. But also water and soil close by informal recycling can be polluted. And next to the dangers, there's also a lot of valuable stuff in there. So some materials we use for electronics are becoming scarce. There are lots of finite materials we use, and some are critical, and that means we kind of depend on certain economies to provide them for us. But if one material is only mined and processed by China, and we need it for the green energy transition, you can see how that might be a problem. And that gives a lot of value to trying to find it within the urban mines, so recycling what we already have. And also mining raw materials generally has a much higher environmental impact than trying to recycle. So that's why we try to recycle electronics as much as possible. And then where I contribute to the circular economy here. So of course you have a mostly linear economy, so production, use, and disposal, and that's what most of the materials go through. And there's a little bit of reuse, a little bit of refurbishment and recycling. And we aim to go to a more circular economy, so more reuse, more refurbishment, and more recycling. And if you know a little bit about the circular economy, which I kind of assume you do, the inner loops are kind of more favorable in most cases, because we don't have to have as much energy input to cycle a product or material. And it just generally has a lower environmental impact. Not for all cases, of course, but generally the rule of thumb is the smaller loops are better. But the problem is that you cannot reuse or refurbish or repair a product forever. And especially with products like electronics, where sometimes the development cycle is very short, we cannot assume everyone is going to repair their old Nokia from the 1990s forever and keep using it, because sometimes it just doesn't really work anymore in our society. And that's an extreme example, but it is the case for a lot of things. So yeah, at some point it needs to be recycled. And that's something that I try to connect to the design phase of a product. So currently recycling mostly happens in spite of product design. Kind of the recyclers try to get out as much as possible. And I'm trying to make sure that the design is actually helping with that. So can we already take this into account in the design phase of the product? And I identified a few challenges in design for recycling. So guidelines should be connected to recycling practice, and I'll come to why that is a challenge later. But yeah, we need to know what we actually design for and what is recycling practice. The guidelines should be adapted to emerging and future technologies in both manufacturing and recycling. So in recycling, if you design a product now, it might be recycled in 10 years. You don't know for sure. And the guidelines should take it into account. And for manufacturing as well, I don't want to make guidelines that only work for this year. I want to make sure we also see a little bit in the future, like what's coming up and how can we adapt that for recycling. Then existing design for recycling methods are not often implemented in practice, which of course is a shame, because if you make a method, you would like it to be used and actually, provide better recyclable products. And there's also tensions between design for recycling and other design for recovery strategies. So you also have repair and refurbishment, and sometimes when you design for one, the other suffers and the other way around. And yeah, those are the main challenges. So my goal is a design guide for recycling, which improves recyclability, is adapted to future tech, overcomes the current barriers to implementation, and addresses tensions between design for recycling and other recovery strategies. So then what I'm working on right now, first is research into common recycling practices. So what do we need to design for? Then what kind of methods already exist? And finally, the most, time-consuming parts for now is the shredding experiments. And I will go into all of these bits more. So first is recycling practice, and just to give you a very simplified idea of how we recycle electronics. You have a phone which cannot be repaired anymore. Let's assume that that's what happens, and not that someone just throws out whatever they don't want anymore. First, what happens is a process named depollution, and it's kind of where you take out all the polluting parts of a product that you cannot just recycle. And in most cases, this includes the battery. Batteries explode when you try to shred them. So these need to be taken out before you throw them in a shredder. And shredding is then the next part. Basically, it looks like this. This is the machine that processes this stuff. And you get all these small parts. And the idea of shredding is basically to liberate the materials. So you have a bunch of materials stacked together, and shredding is supposed to make sure these are all separate again. And then you get to the black box of separation, very simplified. And this is based on different characteristics of materials. So magnetism, conductivity, color, density, etc., etc. Many techniques here. And then you get out metals, the different metals, electronic components, and plastics. And the metals and electronic components are then smelted and made into new metals. And plastics are compounded for new plastics. And there's a lot of inefficiencies in the system, and it's very, very simplified. And the problem with trying to decide what we need to design for is that it more looks like this. This is a very blurry picture intentionally, because I was supposed to keep it secret what's in here. It's a collaboration with Mirek, the e-waste recycler in Eindhoven, and they process about 70% of the Dutch e-waste. And this is kind of a process overview of how they do it. And you can see it's very, very complex. And the problem is that this is just one company in the Netherlands, and also just one category of product. So in this case, this map is for IT equipment. And there's many categories, and they all have their own maps. And it changes as well, like depending on prices of labor, depending on prices of different materials, how much value they can get out of something and something else. So the recycling practice is really not something standard, and that makes it kind of a hard question of what do we need to design for? And what I'm now trying to do is I'm setting up interviews throughout Europe with different recyclers to kind of get a grasp of what are the big differences. So which techniques are commonly used, which are sometimes used, and what makes sense in guidelines. And then, yeah, kind of see what is a common recycling route and what do we need to design for. So yeah, research into recycling practice. The next part is a literature review on design for recycling. So I tried to identify different methods that already exist. And I didn't find so many, unfortunately. There are only 16 that I found. And these are methods, tools, guides, those kinds of things meant to help designers design for recycling. And unfortunately, many of them, some of them are, but many are not really connected to practice or rooted in empirical data, which kind of means sometimes you see a guideline and you look into where it comes from, and it references someone, and then references some guy who just said so. And that's kind of, I would assume, not good enough, because then we don't know why it is a guideline and why it should be important. So yeah, that's also a project for the future, figure out where all the guidelines come from and which makes sense and which don't. They're also not often targeted to design practitioners. Yeah, if you make a design method, you need to make sure that you take into account the user of the method. And that's not always done properly, but yeah. And the final problem is that they're hardly tested, and this is tested in two ways. So tested by designers, who are the user of the method. Is the method usable in practice? Does it combine well with other design requirements? Can I implement this in my work? And the other test is, does it actually make products more recyclable? And this final test is almost never done with the methods. Yeah, so I would like to do that at the end. And when I have this map of kind of common recycling routes and I connect it to the guidelines that I found, I can actually see, are the guidelines we have now in line with how we recycle? And also, is there parts of recycling practice that we do not have guidelines connected to? And should there be any guidelines there? And from there, hopefully, I can start a first version of my design guide. Then the final and biggest part is shredding experiments. So we got very lucky and we got 25 smart TVs for this experiment, 5 times 5 different types. And these are samples from the PROMPT project. This is a European project on premature obsolescence. So for this project, these types of TVs have been disassembled and mapped in terms of disassembly. So we know a lot about how repairable, for example, these products are. And we wanted to do a shredding experiment because, as you remember in the short overview of recycling, shredding is basically what happens to liberate materials. And the more the materials are liberated, the more you can separate out and the purer sort of your end results and the less waste you have from recycling. So if shredding works well, recycling works well, or works better, let's just say that. But we have very little insight in what actually happens in a shredder to products. So what we want from the shredding experiments is insight into the behavior of connection types. So if you have a screw, does it break in a shredder? If you have glue, does it break in a shredder? All those types of different connections. And then in the end, because we already have disassembly maps, we can compare repairability to recyclability and kind of see where the tensions are. This is a short overview of how that went. So, short explanation before. We used an experimental, small scale shredder at Mirek. And because it's a bit smaller than the regular one, the TVs didn't fit in as a whole. So before we could actually shred, we needed to the people from Mirek, we were not allowed to help, saw the TVs in pieces to fit them into the shredder. Yeah, what you see here is basically what we're still kind of working on right now. The box on the right, in the big IKEA box, we had 9 of those with just TV scrap. And now we are sorting out all different materials and especially which connections are still connected together after shredding. Because then we can quantify how bad is it if you put a screw in something, how bad is glue, that kind of stuff. Yeah, almost done. But this I'm doing this together with the graduation student, and she's gonna look at the results soon. And yeah, a lot of work. Yeah, so a very nice picture of one of the Sony TVs, not really intact anymore. We still have to quantify everything, but during the separating, of course, you see a lot of things that go wrong often. Especially glue. Glue is a bad guy here. Things that are glued together, they stay glued together most often. Also coatings, if you have a coating on a material that doesn't really come off. Screws were a bit more of a surprise. Lots of screws actually stay intact in a shredder. Snap fits sometimes. It really depends on the snap fit, and we still need to figure out why some snap fits break and some don't. So that's gonna take some categorization of what kind of snap fits exist and what happens here. And I think the strangest one is steel. So TVs, they have a really big steel frame, which basically keeps them upright. And of course, it has it's important function. But what happens in a shredder is they don't really break depending on the quality of the steel. They just bend. And what happens then is it bends around other stuff. So sometimes you see PCBs that sort of bend in a piece of steel, which means with a magnetic sorting system, the whole thing goes in the steel fraction while you have the valuable PCB in there. That's a very strange experience because that's not 2 parts who were previously connected together at all. So yeah, we're gonna see how you need to design around that or how you're supposed to know. Future problems, I would say. And then next steps is, find out, okay, we have these connections that are still intact, but is it a problem? So we're going with a few interesting pieces. We're gonna visit Mirek again, I think next week, and just ask them, hey, I have this screw in here. Is it a problem for the rest of the process? Because sometimes it's not, and sometimes it is. We have this sticker on a piece of plastic. Is that polluting or is it just all right? So that's the next step. And also a mass balance. So if you have all the materials separated out and you have all the intact connections separated out, you can basically calculate how much of each material is still in a connection somewhere. And in theory, that material is lost. And you can, because we have 5 types of TVs, we can make a bit of a comparison of which TV is doing better and which TV is doing worse. And also make comparison with design for repair, because we have the assembly maps, we can compare, because for example, the screws seem to be doing not so well, but if you want to design something for repairability, it's really nice if you put a screw in because you can take it out and you can put it back in. And then we have a next threading experiment in collaboration with Signify, and it's also a graduation project, and it's basically 5 times 3 types of office luminaires. So if you're in an office and you have these square like things in the ceiling that light comes out of, those things. And because we have a lot more detail about what's in these, we have a lot more information probably. And this student is going to try to make a redesign for improved recycling of these lamps. Then some future plans. So first, construct the first version of the design for recycling guide. Then investigate barriers to implementation. So if I make a guide, I want it to be used. So why are current methods not used so much? Also test in practice. So both with designers on usability, but also on products. Does it make it more recyclable? And also investigate future and emerging tech and the impact on design for recycling. Yeah, thank you. I look forward to feedback and questions.
Thank you. I'll give you a real hand see also some virtual hands already. Thanks for a great insight into the world of shredding, recycling, design for recycling, etc. So if anybody has a question, either raise your hand, or you can also type something in the chat, or you can also just open your mic. At the moment, I see one question in the chat already. Says basically, great practical insights. I can imagine that recycling with a shredder is the way to go with large-scale e-waste recycling, but wouldn't dismantling with robots, etc., result in better and less polluted yields?
Yeah, that's a good question. In theory, yes, but might not be very practical because recycling is a very tight business case. There's very little value in all the materials, and you need to be as efficient as possible. And also, if you imagine the kind of waste that comes in at a recycler, it's just a mix of everything, different years, different types of products, different states. And it's at the moment very hard to design a robot to identify all of that. Maybe in the future. I also look a little bit at Max. Max is working on recycling, of course, and I'm just working on the design part. So if Max, you have a better answer for this.
Max is still very quiet, but he's maybe thinking about an answer.
Repeat the question, please.
It's in the chat. It's in the chat.
Which
So
one?
basically, the question is, so it's all nice to go for shredding, but shouldn't we go for dismantling? Is that not the much better way?
Well, you can do dismantling. So indeed, robots are being used, but the problem is that it's very difficult because every product is different, every waste product. So if you want to actually separate them or dismantle them, then you actually need to have the robot completely set up for that very specific product. So basically, the only companies that can pull this off are the very, very big companies. Like the famous example is Apple. And for anything other, you either need super advanced AI, which will maybe happen in the future, probably not now. And even then, there are quite often still teeny tiny differences, which can basically throw these robots off their steps, which ruins your day.
Yeah.
But if it would work, it would probably be indeed better.
Yeah.
And right now we actually kind of do it. I mean, I think Dorien also already said that the depopulation step, we already do it. It's just human robots.
Yeah, but maybe I was thinking somewhere along the same line. So wouldn't it help if you would design a product in such a way, because you also mentioned, Dorien, that sometimes the valuable products or parts actually come mixed with, let's say, the less valuable parts, and that's just a waste in the end, because probably you're not aiming your recycling for this high grade material or expensive material in these fractions. So wouldn't it be useful if you design a product in such a way that all the valuable stuff, like the real valuable electronic, would be in one part that you can take out directly, and then the rest can be shredded, something like that?
That would be, and also I think that's where Max and my work are kind of connected, because Max would really like to get an entire PCB out so he can do his stuff. And currently we just shred the entire thing, including PCB. So I think Max would appreciate if I put in my design guides, make sure you can take out the PCB in one piece.
Yeah, and that would probably not be that difficult from a design perspective, to be honest.
Well, it depends, because if some products, they have a lot of small PCBs spread out, and there's also a reason for that. It's also in repairability terms, because it's easier to repair one small PCB or to replace one small PCB than the entire thing, and it doesn't cost as much, for example.
But then you could still make one big part, let's say, where all the small PCBs are in, and then you can just take one out and put another in.
Yeah,
I mean,
maybe.
maybe.
And this is also the kind of thing, like, I can say that now, but I feel like I would need to try in redesigning a product before I can just assume that that's possible.
Dorien, you want me to put an example on the screen of the mini small PCBs?
Yeah, please.
Because I've been taking apart stuff, right?
Yeah.
So this is a very famous TU Delft laptop. You've probably all seen them. If you take them apart, I first remove the battery, of course, because otherwise stuff gets exploding. This is what you end up with. So you have one very big PCB, which is where the majority of stuff is located, but you also have 1, 2, 3, 4 small PCBs in this case. And actually, it's kind of cheating what I did here, because technically speaking, the RAM modules are still in the original board, and you could arguably count them as separate PCBs as well. And to be clear, these are usually spread out over the machine. So this relatively big one, for instance, is in a corner where all the ports are located. Yeah. So you want them separately because then probably it's more efficient space-wise inside the laptop, but that's Dorien's domain.
Yeah, but these are all trade-offs, right? I mean, so there is indeed a trade-off if you make it all together, but there's no technical, let's say, it should be. I mean, it's possible. It has some disadvantages, but it's technically possible, I guess, right?
Yeah, but there's also a lot of things that are technically possible, but then economically not possible, because designing is such a business case. If you have to have someone try to find this valuable module in every product, is that worth it for the recycler? That's really hard to say right now. So, yeah, future questions.
Yeah, thanks. I see one hand raised. Yuri.
Yeah, I have a question. Like you said that e-waste is really fast growing, but is there a subset of the e-waste that's growing faster than others, and that maybe focusing on recycling that thing would make, a bigger impact? As in TVs, if I buy a TV, I hope that TV will live for like at least 10 years. If I buy a laptop, at least 5, but maybe a phone only for a year and a half or 2. So is there a point in just focusing on phones, for example, and forgetting about the rest? I'm not sure. I have no idea about the topic.
Maybe. So in the circular circuits proposal, there's 4 use cases kind of pointed out. So you have IT, phones, lighting, and power electronics, I think. I'm not exactly sure which is the fastest growing waste stream, but the idea is that I focus kind of all of them. But maybe also there's also 2 PhDs working on life cycle assessments, and maybe they know more. I'm looking a little bit at Niels, but I'm not so sure. For now, it's just the best to make very detailed case studies, because if you are too general, you don't learn much.
Thanks. Levon? Oh, we can't hear you, Levon. It's very strange noise.
Maybe without the headphones?
Yeah, maybe without the headphones would be better. There's something. Now he's completely gone. Maybe in a minute. Let's start with Erik then.
Sorry guys, do you hear me now?
Yeah, I can hear you. Yeah, Levon.
So I'm from Nina's laptop now.
That's
sometimes my computer does this crazy Mickey Mouse sound. I don't know where it comes from. Nice seeing you, Dorien and Max again. Just a very spontaneous question, idea, I guess. I know nothing about dismantling of electronics, but is there such a approach, I don't know, making instead of using the screws, and which leads of course to manual dismantling, using some kind of, I don't know, glues or metals which are very easy to be melted, so that under high temperature your, I don't know, laptop just kind of melts apart into different pieces, which you can separate much more easily, and then do the recycling, targeted recycling as you were shredding. Just a very spontaneous, naive idea. I don't know.
I don't know. It could be interesting, but the problem is also because if we tried it on a few products, that will not impact recycling of the rest of it. So recycling is a very large scale process. And if recyclers are just gonna shred because most products do not include this, then your idea for new glues doesn't make a lot of difference. And that's kind of the hard thing. If you want to make an impact that also changes the process of recycling, you need to make sure all the products have this implemented, kind of.
Sure. Yeah.
Because you don't really pick and choose, I'm going to recycle this product like this and this product like this. And that's also another complication.
Put a small chip on any device which has the melting parts in it.
I'm going to put it on my list for future tech.
I'm very proud of it that it worked. Yeah. Good luck with work.
Thank you. Erik.
Yeah, thank you for joining this meeting. It's really worthwhile to meet you all. We're setting up a larger growth fund program about sustainable electronics, and recycling is part of it, but also the design rules. So I was curious about what did you investigate already on the design rules topics? So what I see in the examples of shredding, this is really existing electronics. And what do you think about the design rules for new electronics, like using debonding materials and that kind of issues? Can you mention something about that? The new electronic design rules?
Yeah, I'm intentionally not looking at that yet, but it is on my planning because just for scoping reasons, I want to start with where we are now and then branch out from there so I don't make it too complex. So yeah, maybe I can share kind of where can I find this? My current process on existing guidelines. I'm in process of making this giant Excel sheet of what everyone says. So what the guideline is, then how it's substantiated, and then kind of how it's connected to recycling practice, and if there is a context, and it's going to be a very long list, and then I'm trying to narrow down where people agree, where they don't agree, and what still needs work. And I think when I finish that, I know a little bit more about what the first baseline is, about what we know now and what we don't know now. And yeah, when I know that, I can start looking at what happens in the future, I think.
Yeah, sure. But you investigated the already existing electronics in your Excel sheet?
Existing guidelines. So sometimes they include specific electronics and sometimes they don't. Yeah.
Okay, thanks.
Erik, from what company are you representing, or what?
I'm from Berenschot and I'm representing now High Tech NL, and we're setting up I said already a print electronics proposal for years ago, and a branch organization, and now we are looking for a more or less a growth fund program about sustainable electronics. So this could be part of it. And we seriously have to talk to each other, René, to look for some cooperation issues. So this is an invitation for further communication.
Drop me an email and then I'll come back to you. Yeah,
but I don't have a email address, so if you can send that in the chat backwards to me.
Okay, I will do. Yeah.
Thank you very much.
Okay, I see. I see also one question in the chat, and that is by Peter. Yeah, maybe you can just you already have your camera open, so please. Yeah.
Hello, Peter Kwechting from Demcon. You're using shredders. Do they all produce the same size? Can it be rougher or finer? And what's the trade-off in rough or fine shredding?
Yeah, so no, they don't all use the same size. So in this test, I really need to note down, what kind of shredder we use and what size. But you do see when we sort out, there are also a lot of small pieces, and usually we don't see as many like connected materials anymore. So it's usually the bigger ones. But of course, if you shred smaller, you require a lot more energy for it, and also produce a lot more dust. And the recyclers usually already make the trade-off how small or big they want to shred based on that, because the energy goes like this if you try to shred smaller. It gives you pure fractions, but it also, is that worth it? So I've tried to do the shredding test in the way that this recycler usually shreds, to just stay as close to how we recycle as possible.
Thank you for the clear answer. Yeah, and you already take it into account, I think, in your investigation.
Yeah, I mean, if other recyclers in Europe say, oh, we do a very different size, then that would be really cool future research maybe to see. Okay, but then what happens? Also,
Yeah.
this is just the 4 rotary thing shredder, the one that we used. It's not the shredder that everyone uses. So it just keeps getting more complex, kind of.
I understand, yeah, and that's making research difficult to get clear results. Yeah, because it's, yeah, your whole project then diverges, even when you focus on a relative simple and overseeable step as shredding. Yeah, understand. Yeah.
Thanks.
Thank you.
I was also thinking there basically also in my mind there are 2 ways to approach this. So there's one way in that you say, okay, let's make everything modular. Let's make clear that you can disassemble and that you can get the valuable parts out and the parts that you can recycle together out as much as possible. So in the end, because if you go to the true recycling, then of course you run into issues that you don't want to have aluminum if you want to extract copper. So there are all kinds of mixes of metals that you don't want to have in a process that is basically at Umicore, for example. So there are 2 ways to approach this. One is that you indeed disassemble. The other way is that you say, no, I'm going to shred indeed in small pieces, and then I'm going to have separation steps after that makes sure that you do get the similar materials or materials that you can recycle together in certain fractions, so that you have a fraction that you can just sell to Umicore and they can extract the copper and the gold and the silver and whatever, and then you have the iron or aluminum fraction that is going to other processes. So is there any development that you can see in, let's say, this latter route in which you have kind of separation after the shredding that is so good that indeed you have fractions that you can recycle further? Is there anything that you've seen there already?
I am not entirely sure. Maybe this is also more for Max. So
okay.
Max is more the recycling guy, and I just I just try to design. Yeah. Well. Then till the question to you could be so. So indeed, if you would have your design guidelines in place, right, that you're going to produce. So what would ideally a TV set that you just mentioned as an example, what would it look like? You think already? Do you what would it look like?
Yeah.
Well, I think the steel that they put in there would be quite brittle, because we see that some TVs, they don't have the folding as much and some do. So it's not that all steel is a problem. It's just that some use steels that bend lots. Also, I think it would be very nice if they just use connections that if you put a lot of pressure on there, that the materials just in layers just fall apart. And right now, lots of things are glued together in TVs. Some are coated, some materials are coated. It would be better if the PCB can be taken out in one piece, but because the TV is so big and there are ports in all places and there's different functions in places, and also there are electronics like behind the entire screen, I don't think you can have one PCB. But then at least make sure the PCB is not connected with screws or with glue or that kind of stuff. And we even had one TV where there is so much steel in there that the shredder couldn't handle it. So in the end, we only shredded 2 because it just kept blocking. And that could be because it's a smaller shredder, of course, but it also means if you put it in a big shredder, it will require a lot more energy to shred it. So it's still not a very good design for shreddability, I would say. And those are, I think, the first things I would change.
Okay. Yeah. That's good to know. Yeah. And I think that's also what you're looking for, right? For these things that can be, because a lot of the time it's not that the designers of these TVs don't want to think about this, but they just don't think about it because, well, it's not on their list of priorities. So if you can make it a priority on the list of priorities, then it's often with very simple measures you can already achieve quite a bit. Yeah. Peter, you raised your hand.
Yes, well, the discussion we had in earlier in the question, the discussion dismantling or shredding, where dismantling really requires profound knowledge of the parts and etc. But there could be something in between. For example, that you have a TV where you cut off the sides, for example, 5 centimeters around, because the PCBs are in the center and the connections are in the edges, for example, and that you have a generic process.
Yeah.
So something
Yeah.
in between, not the generic rough shredding, but not the detailed knowledge either.
Yeah, that's a very good point that you made, and that's one of the things that I've been involved in a couple of projects on magnet recycling. And magnets are, for example, also in hard disks. And what they basically do is they cut off a corner of the hard disk in which the magnet is present, and all these corners are put into a reactor where they can actually extract the magnet material from it by putting it under hydrogen. Well, that's the whole process, but indeed cutting off the corner in which the valuable stuff is one of those. If you know where it is, you can actually, and this is fully automated. So there's a sensor that senses where the magnet is, and it puts it in the right way in a cutter, and then the cutter just cuts off the corner, and then it goes to the recycling. So these types of things can really help. If once you know where this stuff is, where the valuable stuff is, you can just cut and then make it much easier, I guess. Yeah. Okay, I don't see any further hands raised. I also don't see any further questions in the chat. So I just would like to thank you, Dorien, for this great presentation. Stirred up quite a bit of discussion, so that's really good. Yeah, thank you all for being here during this this session of the LDE Circular Industries talks, and thanks so much to you, Dorien, for presenting your work. And well, there's still 3 years to go, I guess. So there's probably a lot more to talk about in a couple of years. So maybe we can have you back in this series then.
Sure.
Okay. Thank you all.
Have a good day.
Have a good day. Bye-bye.